Let's try to solve this differential equation using Laplace transforms. Okay, so if I apply the Laplace transform here and also there, you have to know that the Laplace transform of y double prime of t is s squared y of s. This capital Y of s means it's the Laplace transform, minus y prime of 0 minus y of 0 times s. So applied to this one, this part turns into s squared y of s minus y prime of 0, that's 18, s times y of 0, that's negative of negatives, positive s. And then what about this one, ay prime, that's s times y of s minus y of 0, but y of 0 is negative 1, so you end up with plus 1. And then plus 25 capital Y of s, because capital Y of s is the Laplace transform of the small y of s. Okay, so that's what you get on the left side. On the right side, you get 13 times, if you look up the table of Laplace transforms, you get s plus 2. It's the formula is 1 over s minus a, but a is negative 2, so you end up with s plus 2. Okay, so we can simplify the left side. You want to solve for capital Y of s, so let's try to put the capital Y of s together. So we have one here, another one here, one over there. So it's s squared plus 8 times s plus 25 capital Y of s equal to, let's see, s becomes negative s if you move to the other side. And then plus 8 minus 18, that's negative 10, move to the other side, it's plus 10. And you still have 13 over s plus 2 on the right side. And you want to solve this for y of s, so you divide by s squared plus 8s plus 25 on the right side. So you end up with 2 fractions. Now, you could bring this into a single fraction. We can multiply s plus 2 top and bottom to the first one to make this into a single fraction. But that's unnecessary because what we are aiming to do is to split them. We want to do partial fraction decomposition, not putting these together. Okay, so this is what we want so far. Okay, all right, so this is what we have. Now what do we want to do? We want to do partial fraction decomposition, and whenever you see a quadratic, you have to first figure out whether this is factorable or not. Is this factorable? No, it's not. In that case, if you can't factor, the next best thing you can do is to rewrite this as a completed square form. So how do you complete the square? You first take the half of 8, which is 4, square, and then plus. Think about what I should put here so that this is equal to that. See, if you have 4 squared, that's 16, right? 16 plus what number would create this 25? And the answer is that it should be 9, right? So this turns into s plus 4 squared plus 9, and you further want to write it as s plus 4 squared plus something squared. 9 is 3 squared, so you want to put it as 3 squared. And this is essential because once you rewrite this using that completed square form, it serves as a guideline to what the partial fraction decomposition should look like. Okay, so you have s plus 4 squared plus 3 squared, s plus 2. Now we want to write down the partial fraction decomposition. This is what we want to do. We want to have something that has s plus 2. Any factor of the denominator would deserve to have a single fraction appointed to it. Okay, so you have s plus 2, so I put a over s plus 2. And then I see s plus 4 squared plus 3 squared appearing twice, but you should only write once. Now why is that? Well, that's because we kind of skipped this part where we put these into single fraction, right? So if we did put this into single fraction, we are only going to see this once. So even if you see this appearing twice, you should only write it once. Okay. So we write it once, and here's the important part. Maybe I should write in red just to stress this. See, if you have s plus 4 here, the partial fraction decomposition should be written as b times s plus 4. And then when you see this 3 here, you should write it as 3 times c. This is very important. Okay, it's somewhat different from the way you were taught partial fraction decomposition when you were doing integration, right? But this is for Laplace transforms, and for Laplace transforms, having your partial fraction decomposition written in this way makes the later calculation much simpler. Okay, it's much simpler if you do that. Okay. All right. So what do? We take this, multiply to, say we have an equation. This should equal to that, and I want to multiply this denominator both sides so that we have the following. We have negative s plus 10. Since this one doesn't have s plus 2 there, it's going to have s plus 2 multiplied, and then plus 13a. When you multiply this to this, s plus 2 and s plus 2 will cancel, leaving you with s squared plus 8s plus 25. And then bs plus 4 plus 3c will have s plus 2 multiplied. Because this doesn't have s plus 2, when you multiply this to that, this parts cancel, whereas s plus 2 is the survivor. All right, so that's what you get for the partial fraction decomposition. Now we have to figure out what a, b, and c are. Okay, so we have this following thing. How are we going to find a, b, and c? Well, first, I realize that if I have s equals to negative 2, both b and c just disappear, just like that. If s is negative 2, it goes away, right? So, and also if s is negative 2, this also goes away. So you have a very convenient thing. So if s is negative 2, then 13 is equal to, let's see, negative 2 plus 4 is 2, 2 squared is 4, 4 plus 9 is 13. So you have 13a, which is a equal to 1. Now, keep in mind that this equality here is an equality between functions of s. So this is a function of s on the left side, this is a function of s on the right side, and we're trying to say that both sides are equal. And therefore, you're allowed to plug in whatever value to s, and that property is what we are using to find a, b, and c. Okay. All right. Now the next best number you can plug in is negative 4, because if you plug in negative 4, this becomes 0 and b is gone, right? And you'll still have c there, you'll still have a there, but that's still fine. Okay, so let's plug in negative 4. Let's see, negative 4 is 14. Negative 2 times 14 is negative 28 plus 13. That's negative 15 on the left side. Negative 4, that disappears. It'll be 9 times a. And then this disappears, and 3c, let's see, negative 4 plus 2 is negative 2. Negative 2 times 3 is negative 6c. And remember, since a is 1, I can replace a by 1 and move it to the other side. I get negative 15 minus 9, which is negative 24, equals to negative 6c, giving you that c is 4. All right. Now, we don't have any good numbers to plug in. You can't plug in s equal to anything to delete some of these. In that case, there are two ways to go about it. One is to plug in other numbers, something that's simple, easy to calculate. I think s equal to negative 1 or s equal to 0 could be a good choice. You can do that. Okay. However, there's another thing that you can use, which is a property that if two functions are same as polynomials, then when you organize it in their orders, then their coefficients should match. Actually, that's what we were using when we were solving equations using power series methods, right? So if we were to expand this, it will be negative s times s, so you get negative s squared, and then you're going to have something times s, I don't know, something. And on the right side, let's try to hunt for s squared. There's s squared times a, so there will be as squared there. There would be bs times s, so it's b times s squared. And then you get something s or some constants. So you get something more, okay? Now, I'm going to be lazy, and lazy is good in this case because we don't have to use other things. We just need one more equation, right? And the thing that I see is that on the right side, you have a plus b times s squared. On the left side, you have negative s squared, okay? And that should equal because the two sides are equal as functions. And therefore, you have negative 1 equal to a plus b. And then plugging in a equal to 1, you get b equal to negative 2. Awesome. So we got a equal to 1, 4, c equal to 4, and b equals to negative 2. Now, such a method I like to call compare the highest order coefficient. So highest order coefficient. Alright, so we got b equals to negative 2, c equal to 4, a equal to 1. What do? We have to go back and plug it into our thing here, right? A is 1, b is negative 2, c is 4. Right, if I plug that in, this is what we get. We get, since that was our y of s, we get the y of s in this form, 1 over s plus 2, negative 2, s plus 4, 3 times 4, okay? And then this means that this is not what we want. We want y of t. Y of s is the Laplace transform of y of t. So in order to get y of t, you have to take the Laplace inverse transform. The inverse transform, you just have to look up the table to see what corresponds. So this is what we get. And then we can now see what Laplace inversions are just by going back to the table. So this one here is e to the negative 2t. The 1 over s minus a is e to the at. So it's this here is the Laplace transformation of e to the negative st. This one here, you'll see that it's the Laplace transform of negative e to the negative 4t cosine of 3t. This 3 comes down here. 4 becomes negative 4. And this one here is plus 4. 3 and 3. If these two match, then it's e to the negative 4t sine 3 of t. Okay? So that's your y of t. That's the final answer. And this answer was easily obtained just because the way we did the partial fraction expansion. You know, a lot of times people just learned it this way, that in integration, when you have something like s squared plus 8s plus 13 like this, they were told that you should just do b times s plus c. And that's actually, I mean, it does work, but if you do it this way, then you'll have to go one step further in order to figure out which one works. Okay, so please try to use it in the form of bs plus 4 plus 3c, where the bottom one is in a completed square form in this form. Okay, so bring this up there, bring this up there. Okay, hopefully that helped.